I'll keep it short then. Okay. Thank you all for attending this masterclass today, and I'd like to thank MINEX for giving me the opportunity to give this presentation today. First, I've got to apologise. My presentation is only in English, but there are some pen drives or memory sticks at the back of the room which we have the Russian translated presentations on as well for the Russian speakers. So my presentation is on adding value through appropriate integration of hydrogeology and rock mechanics studies. On the agenda for this presentation, before we get into the actual discussion about the integration of hydrogeology and rock mechanics studies, I'm going to discuss or tell you about what a geotechnical model is, then discuss or again tell you how you should plan your geotechnical drilling and your field investigations, then the value that you really get from an integrated mine planning, and then a short discussion on some of the new technologies available which can really add value to these studies. So the geotechnical model is the fundamental basis for open pit mine design and underground mine design. It's composed of individual regions, each of which is comprised of materials exhibiting internally similar geotechnical properties. The parameters are assigned to each domain and should reflect the engineering properties of the rock mass based on your field logging and your laboratory testing. And the design strength values should be determined to input and support both the open pit and underground mine design. And really, this geotechnical model needs to be a combination of your structural model, your geological model, and any alteration modelling that you do, the hydrogeological model, and then the rock mass model. And it really forms the basis for all optimised pit designs. And the sources of data available primarily are your drilling, and then the outcrop mapping, and then the more sophisticated techniques like geophysics. So I'm just going to talk you through what we see as a rock mass model constitutes, then the geological model and the major structure model, and then a bit more on the hydrogeological model. And really that rock mass model should define the engineering properties of the rock mass. So you're considering the intact rock strength, the rock mass ratings, the shear strength of the rock mass, and how it's going to behave from an engineering perspective. And you really need to understand what are going to be the controls for that rock mass. If it's a strong rock mass with relatively few fractures and high RMR, and then the structural controls are very critical to your pit design. And it's the failure along the joints and the bedding faults that are really going to affect the design, and really that's how you design your bench and inter-ramp scale. And you really need to get a grasp of the strength, location, and orientation of these structures. And for a weaker mass deposit, it may not be the structures that will be used to define how the rock is going to behave, and it might well be that the rock mass strength will define how the rock mass behaves, and that needs to be considered for your pit design. So the images here, you can see in the top, we have a large structural failure in quite a high rock mass strength, competent rock mass. And then the bottom here, we have a weaker rock mass where you've got a larger failure actually through the rock mass. And you really need to understand each type of failure for your rock mass model. So I said these are some of the geological models, the alteration model and the structural model, and really you need to understand these for your geotechnical model, and you have to have a good understanding of the different rock types, the geometry of the resource, and any weathering that may affect the rock mass. Another important element to understanding the alteration is the alteration model, because that can have a detrimental impact on your rock mass and subsequently your pit slope design. And you require a 3D model, for different ore body and waste rock types. And the major structure model is also something that's very critical to your geotechnical model to understand where these large faults and structures may lie in a pit. And it's really these large-scale structures that will influence the overall and inter-ramp angles rather than your bench-scale geometry. And the final element to your geotechnical model is understanding the hydrogeology and the groundwater conditions. And there are state-of-the-art softwares available now to understand the groundwater conditions for the mine. And these can be coupled with geological models using software packages such as Leapfrog to develop a 3D hydrogeological model. And it's worth pointing out here that software is not enough on its own, as experienced engineers are required to build and interrogate a groundwater model. So that's really the 4 elements, or 5 elements to the geotechnical model. You have to have an understanding of the geology and the alteration, the hydrogeology, the major structures, and your rock mass model. And they really form the basis for defining your geotechnical domains. And the parameters you should assign to these geotechnical domains are listed here, and you should really understand the material type, the alteration degree of alteration, major structures, any fabric or jointing, rock mass strength, your elastic modulus for your rock mass, and then also your pore pressure information. And these should be assigned to your different domains in your geotechnical model. And so once you've developed that geotechnical model, it's really then that you can undertake your slope design or your underground mine design. And this image here is just an open pit where we have carried out some state-of-the-art leapfrog modelling to define some of the areas where we have poorer rock mass conditions in comparison to the surrounding waste material. So that brings us on to your geotechnical drill planning and field investigations. And the one thing that I've highlighted here, apologies, is that your deposit type is the key. You need to understand if you're working with maybe a copper porphyry where you have a column or a column-shaped mineralization, or whether you're working with a flat-bedded phosphate deposit or coal deposit, or whether the deposit is a shear-hosted gold vein, because that is really what will drive how you plan your geotechnical drilling. And where the value comes is really integrating both your geotechnical studies and your hydrogeological field programs, so that will maximise your data and minimise the drilling times and costs. And where we're seeing or adding more value to projects recently is partnering with the resource drilling and collecting geotechnical data from the resource drilling, and then subsequently using the holes after they've been completed to do hydrogeological monitoring and groundwater and testing. So you really need to determine where your geotechnical data and hydro data is needed, target the waste and your mineralisation, also production and final pit walls. And as we said, for the drill holes, you need to think about the location and length. For instance, for a resource drilling program, you might be just targeting the mineralisation. Whereas if you're going to save money and cost and time, why don't you drill the hole an extra 20 metres into the waste material, and then you have a geotechnical hole as well as a resource hole. Second thing you need to think about is azimuth and inclination. If you orientate the hole for your resource drilling, you can then use it as a geotechnical hole and collect structural measurements. And the third thing I have there is diameter required for hydro testing. Normally the holes need to be slightly larger for hydro testing, and these holes should be considered when planning any kind of field investigation. And the logging parameters that you should collect, just listed a few here, are your rock mass classification systems like RMR, alteration logging, weathering grade and intensity, rock mass strength, major structure logging. Also, if the holes are going to be used for geomechanical sampling, and also get a good understanding of the fracture logging, because that will have an impact on how the hydrogeological conditions will be affected. And I've got this slide in here which just shows, as we said, the resource drilling may just target the mineralisation shown here in red. The geotechnical drilling needs to be slightly deeper and target the waste for the pit slope design. But the hydrogeological field investigation needs to consider the area outside the pit, because that all feeds into how you develop your hydrogeological modelling. And these are some of the systems available for hydrogeological field investigation. One of the systems that we use quite a lot for deposits, especially when poor pressure is an issue on slope designs, is the borehole packet testing. But as I said, these are all systems available for hydrogeologists to carry out their field investigations. This is a packet test that we carried out on a project in a 55-degree inclined angle. And it's needed, it's a packet test, and it's needed in projects where hydraulic conductivity is low and vertical variation exists. Low permeability often implies difficult problems in the pit walls depressurization. And really what the packet testing will do will give you an understanding of the hydraulic parameters and the vertical variation across the rock's mass. As I said, they usually use larger diameter boreholes, supplemented with smaller holes that need to pair up for the hydrogeological monitoring. Usually the hydro field investigations need more time for implementation, and because of the duration of the drilling, testing and seasons. And we've just got a point there, it usually requires more than one contractor and may require equipment, import and shipping, so often, surprisingly, more expensive than anticipated. So that's really the understanding of the geotechnical model and how the hydro, geology, major structures, alteration modelling all feed into that geotechnical model. And if you can get a good understanding of that geotechnical model with high confidence, that will then really add value to your project. So when you get into this stage, which my colleagues have spoke about earlier, about the actual mine planning, if you have a high confidence, reliable geotechnical model, then that will really add value to the project. So what I'm going to discuss now is how we integrate the mine planning and the benefits of that then it will have on your pit slope design. And these are the three disciplines that I see for this mine planning. The mining engineers, the geotechnical engineers, and the hydrogeological engineers, and the elements they do for a pit slope design. And these really feed into each other in that we need to understand what the factor of safeties are and the probability of failures from the mining engineers and what kind of risk our clients are willing to accept. Also need to have the pit shells, whittle pit shells that we spoke about earlier from the mining engineers before we start to do our slope design. They also feed into the hydrogeological modelling, and one of the elements we have there is the cost of dewatering and time of dewatering, which needs to feed into the mine planning. And then what we get from the hydrogeological modelling is pore pressures, and specifically in weaker rock masses this can be very critical to any pit slope design. And then we'll give design factors to the hydrogeological modelling. I've touched on factor of safety and probability of failure, and these are just some acceptance criteria for internationally based pit slope design, and you can see how they range from kind of 1.1 through to 1.5 based on whether it's the bench design, your inter-ramp design, or whether it's the overall pit slope design. And just want to bring your attention down to these bullet points. Here, I've labelled that other approaches to slope design apply the factor safety material parameters, and that's really based on something like a Eurocode design, where you would apply your safety factors or your factors of safety to the material parameters. And specifically for a Russian Design Institute PROEC design, that's a similar kind of approach, where you apply your safety factors to the material parameters, and then the limit equilibrium analysis then is based on a value of 1, where if the limit equilibrium analysis result is less than 1, it's unstable, and if it's above 1, it's stable. So that's very important. I want you to bring that to your attention, because there are different approaches to these designs, and SRK can do both. The SRK, the Russian Design Institute PROEC design, and the international designs. And this is just another mine planning flow diagram that I've tried to put together to really give you more information on how I see it, or we see it, for this integrated mine planning design. So as we said, there's initial pit design based on the reserve, and the mining engineers work out and optimize the pit shell, as my colleague Fraser explained to you this morning. From that then, there will be a field investigation, geotechnical and hydrogeological field investigation, and our hydrogeologists will carry out some initial groundwater modelling and try to understand what the current phreatic surface or groundwater surface is at the deposit. We will then take that and import it into our slope stability analysis and try to work out what the slope angles are for this initial design phase, phase 1 we'll call it. And after we feed that back into our mining engineers, they then would carry out a more detailed design of the pit. And it's really in here then that we start to see the more optimized pit design, in that the mining engineers would provide a final pit design and a life of mine plan and give this information to us as give it to the hydrogeologists. They would then carry out detailed numerical modelling to understand the impact of the mining on the groundwater level over the life of mine. And it's really only then that we get a more realistic understanding of the groundwater conditions for our slope optimization. And we would input then the pore pressure grids to really try and optimize that slope to give the steepest permissible slope angles for the design. So that's really, as I see it, or as we see it at SRK, as the design phase to integrate both the mining engineers and the geotechnical engineers and the hydrogeologists to really give our clients with the best slope design possible. And I think this is where you really add the value from the integration of these different disciplines, because they cannot be done in silo, they cannot be done individually and independently, and really need to be done as an integrated mine planning. So I'm just going to talk you through some of the elements for the different disciplines. As I said, for the phase 1 hydrogeological modelling, we would carry out a field investigation and try and work out what the existing groundwater level is at that deposit, and then try and give some consideration to how it would change in respect to the open pit. And usually we generate a 3D groundwater level surface for consideration in the pit slope design. And here we can see we have an existing groundwater level which usually has some drawdown to the toe of the slope. And it's really, this is the kind of initial phase of the hydrogeological modelling or understanding of the deposit. For the phase 1 geotechnical slope stability analysis, we usually do a high-level slope stability analysis using limit of equilibrium. Sometimes we can use more detailed numerical modelling packages that do finite element, but more often not, the LEA is sufficient for a deposit. And we develop simple geotechnical domains that reflect the rock mass conditions. And usually what we try and understand here is the impact of the groundwater on the pit slope and whether it is critical to the pit slope design. For instance, if you're working in a hard rock, competent, low fractured rock mass, the groundwater will have very little impact on the slope stability analysis. And that shows us you don't have to spend too much time on the numerical modelling for the groundwater because it's not very important to the slope design. And what we're trying to do is a sensitivity analysis and work out the impacts of it being dry, partially saturated or wet. Although it's not very clear on this flow chart, on this diagram here, it's just trying to show the different factors of safety for the limit of equilibrium analysis to see the impact, and if it's critical for the groundwater on the pit slope design. That then is fed back into our mine planners, who then do a more optimised pit slope design and create a mine excavation sequence for the life of mine plan. And that's given back to a hydrogeologist then, and if critical, to the pit slope design, and certainly for dewatering of the pit slope, they will carry out more detailed numerical modelling of the groundwater conditions. And these are just some, these are just some of the main numerical groundwater packages available that we use to understand the change in groundwater conditions. And I've kind of touched on this before. It's very important that the software is not enough on its own, and there is a need of experienced engineers to build and interrogate a groundwater model. And the example I have here on this image is an unstructured grid USG of a mudflow model, which works out the change in groundwater conditions over the life of the mine. And it's really only then, after we've done the detailed numerical modelling of the hydrogeological conditions, that we can do a more detailed slope stability analysis. What we see here is a detailed slope stability analysis containing different rock mass domains. We have different groundwater levels. So we have an average groundwater level, a low, or best case, and worst case. And it's really at this stage in the phase 2, after input from the hydrogeological modelling, that we can carry out more sophisticated analysis, such as probabilistic analysis, to understand or account for the variability in geotechnical conditions. And it's really at this stage that you can provide actual groundwater conditions, so we will know what the models tell us, what the groundwater conditions will do as the mine proceeds. And it's really here that if warranted and is critical, we could use pore water dissipation modelling to reflect the changes in permeability and rock mass and how it affects the slope stability. And it's really important that everyone works together at this stage and cross-checks and validates data between the hydro and the GT models to explain that relationship between the structure flows and the permeability of the rock mass. And as I said earlier, a reliable geotechnical model that takes into consideration the geology, the hydrogeology and the structure is crucial to the design. And you must agree on the prevailing or controlling hydrogeological and geotechnical factors and parameters, and work out what controls the design, whether it's the pore pressure or whether it's a blasting effect. And again, I come back to this again, avoid duplication, save time and resources. And this image here is just some pore pressure dissipation modelling to show how the change in groundwater conditions are for the pit slope design. And if it warrants it, mine depressurization could be used to try and reduce the amount of groundwater pressure or the effects of groundwater pressure on the slope, and that will then maximise your slope angles and reduce stripping costs. Avoid impact on the mine production due to water inflow and reduce health and safety risks, environmental impact and related costs. I'm running out of time here, so I'm just going to flick through this next slides. So as I said, the groundwater can change the effective stress and result in pore pressure exerted on the rock mass. And any increased pore pressure reduce rock mass shear strength, increase potential for instability. And the effects of the groundwater on rock mass strength will vary across projects, and really need to understand the impacts and what's critical to the pit slope design, especially in weaker rock masses. And I guess this is the slide that really everyone should take into consideration, because really any kind of increase in overall slope angle over a conventionally designed slope, as we said earlier, if you can increase the overall slope angle by just a few degrees, these are the kind of percentage increases you're going to get in your reserve, and also the percentage decreases in waste stripping. So you only need to increase the overall slope angle from an appropriate integrated geotechnical and hydrogeological field study, and you can see the kind of savings you're going to have on your waste stripping and your reserve. So I've got a few technologies here. I'm just going to flick through them very quickly, so I won't have much time now. The acoustic televiewer is a fantastic bit of software that we've trying to use more in Kazakhstan. It is used internationally, and it really gives you a good understanding of what the actual rock mass structure is like. You know, we're still working on projects in Kazakhstan where you use the core integrator tool, which has a lot of variability and often, more often than not, ends up in a conservative pit slope design. So this is a technology that we would recommend for any of our studies. I touched on earlier, leapfrog modelling. There are applications on leapfrog which will enable you to carry out 3D geotechnical wireframe modelling, and we're using these more and more on our projects. The 3D models can really show the variability in the engineering properties for the rock mass, and what I'm showing here is a 3D geotechnical model showing the variability in rock mass rating for a copper porphyry deposit. And the final technology that I've got to show today is remote geotechnical mapping, where we have photogrammetry, LiDAR and ELF photogrammetry, and these are all methods that allow remote geotech data collection. And there are systems available to map the benches after you've collected the data using photogrammetry or LiDAR or aerial drones, and that will give you a good understanding of what your small-scale structure, your joints and your structures, major structures are for the deposit. And again, this is a technology that we use on projects throughout the world, and we have used them on projects here in Kazakhstan and in Russia, both for, well, only for operating pits. And what we tend to use them, where their value really is trying to optimize pit slope designs on operating mines where you don't have any geotechnical data. So my final slide, consideration to geotechnical and hydrogeological studies should be given for any open pit design and certainly for any underground mine design. And the early integration of the geotechnical hydrogeological considerations into drilling and field investigations will save money and time. If you have a resource drilling program, I don't see why we're not collecting basic geotechnical parameters and hydrogeological parameters from your resource drilling. Why do we wait until we've defined the resource and then remobilize rigs, pay more money to bring the rigs back out onto site to do specific geotech holes? Why can't we integrate it all and really save money and time? And there are new techniques available and equipment to increase the accuracy of the data and reliability in those results. So them technologies there will give us more confidence in our geotechnical models. I said there is state-of-the-art software available, and it needs to be combined in iterative analysis with interaction from the geotechnical engineers and the mine planners to maximise slope angles and save money. I'd like to thank you all for listening. I've kind of rushed through that presentation a little bit, but I'd be happy to take questions either now or over lunch. We've got time for one question.
Спасибо за доклад. Но вы достаточно подробно осветили вопросы геотехнологии на открытых горных работах, ничего не сказали о подземных работах. Поэтому, естественно, возникает вопрос о подземных работах. Почему? Потому что для систем разработки на подземных работах огромное значение имеет предварительное знание о поведении пород. Ну, допустим, камерно-звуковая система, это пилос, или блоковое обрушение, блок кевинг, или самообрушение, или принудительное обрушение. Так? Когда при камерно-звуковой системе надо предотвратить обрушение и разрушение, а при блоковом обрушении или самообрушении, наоборот, надо вызвать обрушение и разрушение. То есть это разные вещи. Об этом вы ни слова не сказали. И я хотел бы, конечно, получить ответ, как используется теория Винявского локшера при определении шага обрушения, при определении возможности обрушения. Это было бы очень хорошо, потому что здесь много подземщиков сидит. Открытые горные работы сами собой интересны, но у подземных горных работ есть свои интересы и свои большие проблемы. Ну, что касается гидрогеологии, вы, наверное, должны знать, что самые большие в мире водопритоки подземной горной выработки находятся на территории бывшего Советского Союза. Это Мегалимсайское месторождение в Южном Казахстане, где ваш покорный слуга работал 16 лет под землей. Там притоки достигают между, то есть когда малые притоки, это осенью и зимой 7-8 тысяч кубометров в час по горизонту. А вот паводки, это весна-лето, 40-50 тысяч километров в час. И североуральские бокситовые рудники в России, где водопритоки достигают 10-15 тысяч километров в час. Мы разными способами боролись с этими водопритоками и достигли прекрасных результатов и работали нормально, добывали огромное количество руды. Ну, североуральские бокситовые рудники продолжают еще. А что касается открытых горных работ, самые большие притоки в мире, самые плохие водопритоки в мире, это на Жайремском месторождении, далее западный карьер, где воды карьера представляют собой агрессивные кислотные воды. И ваш покорный слуга строил как раз водозащиту вокруг этого карьера, и мы тоже этих успехов нормально достигли. То есть в Казахстане гидрогеологам есть чем похвалиться. Мы это делали вместе с Российским институтом геогем, который, по-моему, присутствует здесь и должен какой-то доклад. Спасибо.
Большое спасибо докладчику за комплексный доклад по геотехнологиям. Большое спасибо задающему вопрос. Я как раз в студии АКИМ являюсь директором института целесообразной. Вот у меня вопрос такой. Я вижу, что у вас подход правильный, комплексный для оценки всех геотехнологических факторов, влияющих на принятие решений. Это требующий большой набор специалистов разных областей. Существует ли практика создания совместной модели прогноза рисков гидрогеологических, геомеханических, инженерно-геологических и горных? Совместная модель прогноза рисков, которая даст потом проектировщику и горняку достаточно информации для принятия решений, поскольку все это изучение должно вылиться в конце концов комплексной оценки горной ситуации. Спасибо.
Short answer, no. I haven't seen a specific rock mass model. I think what we try to do at the early stage of any kind of project, at the proposal stage, is try and have this meeting between different disciplines to work out what are the risks to the project. For instance, you can tell very early on if it's a weak rock mass that's going to have high groundwater levels, then getting a good understanding of your groundwater conditions for that particular deposit is critical. And that's why we said on one of my slides the deposit type is key to understanding how you're going to carry out your analysis. And really we try and have these integrated meetings at various stages of the project to really ensure that we are capturing all the risks necessary. But I agree, a rock mass, a risk model would be something interesting and something maybe we could think of for a technical paper or something. Okay, any more questions? No? I think that brings us on to lunch then. Thank you very much for your time.